wait for a couple.
Yeah, no problem. It's the law of nature that seminars never start on time.
Taking our time, usually it's 90 minutes here, but yeah, feel free.
Yeah, I don't know how long this talk is, so ask me questions.
Hi, Kartik. Can you hear me?
Yes, hello.
Hi.
Yes,
sorry, I'm
Zoom.
stuck. Yeah, I'm stuck at home due to some personal issues, but yeah.
Oh yeah, no problem. No, I went to your office and you were not there, so I just emailed you.
Yeah, no, I know. Yeah, I replied. Yeah.
Yeah.
Maybe we can get started. Welcome everyone to today's seminar. We are very happy to have Kartik Prabhu with us today. He's going to tell us about computing infrared observables and scattering. Yes.
Okay, thank you for the invitation. Yes, I'll talk about how we can try to compute infrared observables in scattering. Notice I've not said infrared safe observables, I've said infrared observables. I'm going to count actual IR observables. And feel free to ask me questions, stop me anytime something is not clear. So what is the problem? So we're looking at scattering, and what really scattering we intend to do is we want to send in something from the far past and let it do its interactions, whatever they may be, and see what you get in the far future. So that's the scattering formalism in very naive terms. And the way you do it is you use an idealization, which here I'm going to take asymptotic flatness. If you're changing your asymptotics, you can do other things, but let me just consider asymptotically flat spacetime. You can think of this as Minkowski if you want. And to make this sort of notion of past, future infinities more rigorous, it was given by Penrose's conformal completion construction, which basically is you just imagine some kind of diamond of that sort. This is one dimension reduced. So there's time going upwards, space going left and right, but one dimension of space has been ignored in some sense. And you do a conformal transformation, bring all the infinities to a finite place. So you attach all these boundaries. So there are null boundaries. There's this big sphere at space-like infinity. And there are also boundaries at time-like infinity, I plus and I minus. And Minkowski, or any asymptotically flat spacetime, sits inside this diamond. And so for scattering, you can imagine you're sending in some particles. So if you're sending in particles or massive bodies, they'll always come in from past time-like infinity. Any massless particles or fields will usually go to null infinity because they move in null directions. And so you send in something, it does some complicated dynamics, goes out, but in the middle, it emits some massless radiation. So mostly here I'll be talking about the problem that arises when you include massless radiation in your whole scattering problem. So what's the problem? The problem really arises in 4 dimensions when you have massless fields because of something that now is called the memory effect. And here's sort of a cartoon diagram of some gravitational wave signal. This is not real data from LIGO. I don't have access to those things. So if you think of some sort of stress tensor or some gravitational waveform going out to infinity, and the signal usually you get is there's some oscillations and there's some big peak where your black holes or stars or whatever collapsed into one object. And generically, what is expected classically is that you don't go back to the original value that you started with. It doesn't matter if the original value was 0 or not. It's just that there's a difference between the value you started measuring it, and then you end up, after this whole signal has passed, all the gravitational radiation has passed, you no longer get these oscillations, but you end up at a different value. Here it's very, very exaggerated. It's not, the signal isn't this big usually. And this change between the value at when you started and when you end up is a function of angle, and it's called the memory. So this is purely classical right now. And generically, the memory is non-zero. And if I write that in Fourier space, if you imagine this idealized as some sort of step function, it's not really a step function, there are small oscillations. In Fourier space, that behaves as 1 over frequency. That's the main contribution from the step-like piece. The oscillations will then contribute other higher order terms, but this 1 over frequency is the big problem. And the reason it's the problem is if you compute your usual 1 particle Hilbert space norm of something like this, so this might be familiar to most of you from QFT class. You just square integrate with the correct measure for massless particles in Fourier space. If you convert this formula into frequency and angles instead, you get this. So here omega is the frequency of this null momentum that I had, and k hat is the direction on a sphere.
It's going like 1 over omega and small omega?
Small omega.
That's not the step function. I mean, a step function, if it has a big jump, it's 1 over omega at large omega. This is some...
No, I mean, so for a step function, it would be exactly some principal value of 1 over omega, roughly speaking.
That comes from discontinuity in the step.
Okay, so if you take, tan hyperbolic or something, you'll still get a 1 over omega. It's not a low this really is a low frequency problem. And it's coming because your function, even if it was assume it's decaying to 0 in the past. It doesn't decay to 0 in the future. It goes to some non-zero value. Okay, yeah, so one way to see this is what we're talking about is the difference between the value of h at minus infinity and plus infinity, right? So I can write that as the integral of time derivative of h.
Yeah.
Okay, so now if you Fourier transform everything, you will see that its time derivative has a non-zero value at 0 frequency. So the time derivative has a non-zero value. So now if you go back to the Fourier transform of the original h, you get a 1 over omega times something non-zero. So that's the...
I epsilon, omega plus I epsilon, and then you can see.
Sure, yes, you could...
Positive time it goes upon to 1 and in 1 you come an acceleration.
Yeah, you'll get a difference between the values and the 2 points. Yeah, that's another way to see it, yes.
And value need not be 0, it just has to be different from delta.
Yeah, it will be, this delta is just the difference between the values. Whether the initial value was 0 or not really doesn't matter.
There's non-zero as a classical.
Yeah, so far this is just classical. I'm saying now if you say, I'll get these signals at least classically. What happens if you try to do some quantum stuff on it? And naively, this norm, the 1 particle norm that you'll put on it, will diverge. So if you put h as 1 over omega here, you'll see that it will diverge. And this doesn't happen in any higher dimensions because this scaling with frequency changes in higher dimensions and it helps you out. In 4D, this omega is not enough to help with the 1 over omega squared coming from you, right? So for example, you can say, okay, I have a classical signal. Let me convert that to a coherent state, right? Any classical solution you can convert to a coherent state. And that coherent state will have diverging norm in your standard norm that you use.
So this seems to be a problem with the law, not necessarily with the physics.
Exactly. Yes, that is exactly the point I'm going to make.
The number of gravitons is infinite, but not the constant.
Yeah, so the energy is finite. Even if you compute angular momentum, it's finite. Everything is finite except particle number, right? So it's not a it is a physical effect that this jumps, but the problem is not that this effect exists. The problem is with this norm that you're constructing. And I'll explain that more. Any other questions? Okay, so what really is happening when you quantize? And this is related to what is called the Weinberg soft theorem. It's exactly the same effect. So when you try to do scattering, usually you have some in-state, you say, okay, I have some S matrix operator, I act on the in-state, I'll get an out-state. That's the job of the S matrix in QFT or quantum mechanics for that matter. Now, Weinberg's soft theorem tells you that if you compute these S matrix amplitudes, you get a 1 over frequency divergence. So if you can write this out explicitly in terms of amplitudes if you want, but whatever you put in here has at least some part which is 1 over frequency divergent. And so your out state will also be 1 over frequency. So even if your in state was super, super nice, you made some nice small wave packet or just massive fields, electrons and positrons or whatever, but your out state after scattering, both the classical theory and Weinberg's soft theorem is telling you it will have diverging norm. Okay? And like Raghu was saying, this seems to be a problem with the norm, not the physics. And that's exactly what's going on, is states which have this memory effect, where the final and initial values are not the same, they're displaced, they actually live in a unitarily inequivalent Hilbert space of your field algebra. Okay?
It's also confusing because if you're saying that a physical experiment can create memory, how can it be in a different Hilbert space?
Why?
I mean, you're doing some experiment and in principle this is measurable.
Correct.
So what does it mean to be in a different?
It just means that it's allowed to emit an infinite particle number at small frequencies. So, in standard QFT, we have this notion of, okay, we always have one God-given Hilbert space or something. And that's not true here, is what I'm saying. I mean, it fails in other contexts. It doesn't work if you do QFT in curved spacetimes. There is no unique Hilbert space. So in flat spacetimes, we've kind of gotten lax because we have a nice invariant vacuum. And that's the Hilbert space we work with.
We call it Hilbert space.
Sure, you can do union. For Hilbert space, there are many things you could do. So for example, you could do a direct sum over all infinitely many of those. So you would say, okay, that is fine. What that doesn't allow, so here, this memory will
Sorry, Kartik, I have a question. Can you hear me? Sorry, can you hear me?
Yes, I can hear you.
Okay, sorry. Yeah, the question is actually, so, I'm sorry, I always find it hard to translate some of this language. If I think of sectors with a fixed super translation charge,
yes,
then is that the same as thinking of these F deltas? Like, can I think of the super translation charge as corresponding to these deltas?
No.
Delta of K, no?
Yeah, I'll explain the super translations charge business when it shows up.
Okay.
But the short answer is the super translation charge, we believe, is conserved.
Good. So this I should think of this as the zero mode of the shear. Is that I should think of it as the conjugate of that? Is that how I should think of it?
No, so this isn't the zero mode of the shear. The shear looks like, this jump, the step function jump. So it's not a zero mode in the sense of constant.
I see. Sorry. Yes, I'm. So maybe you'll answer this question later. I was just trying to understand in that language where I think of the Hilbert space as breaking up into sectors of different super translation charge. How should I think of this degree of freedom?
Okay. So
You can explain later if it's more convenient.
yeah, no, I'll give you a quick answer and then I'll explain when it shows up in one of my slides. The quick answer is in gravity, all eigenstates of the charge, which are not the invariant vacuum, are all non-normalizable states.
Okay.
They're all improper states. So if you make sectors of super translation charge, all your states in there will not have any reasonable norm.
Well, they're delta function normalizable.
Yeah, so that's what I'm saying. They're improper states, right? So
Okay.
now if I say, okay, you have all these improper states, like momentum states, right?
Yeah. Yeah.
Usually what we do is we make a wave packet out of them by integrating them with some.
Yeah.
Okay, it's not known how to integrate over the super translation momenta or eigenstates.
Sorry, why I just put a wave function as usual, like I do in other situations.
What's the measure of integration?
It's a delta function normalizable thing, so I would have thought it's just delta s minus s prime is the norm, and then the measure of integration is just ds prime. Is that wrong? You're saying that's not correct?
Yeah, so you have infinite number of super translation charges, so you have to
Yes.
write a measure on an infinite dimensional space.
Sure, we do that all the time. Like I convert it to spherical harmonics, and I write down wave function for all the spherical harmonics.
Yes.
So that would be okay then.
That would be one Hilbert space you can make, yes.
I see. And could you please tell me how does this mode correspond? What would it be in that Hilbert space? Like, is it simple to see what it would be in? Like, what's the degree of freedom in that Hilbert space?
Yeah, okay. So the super translation charge is which we are asking about, is the memory plus what is usually called the hard charge or the News function squared.
I see. Okay, so this is the soft part of the super translation charge.
Yeah, so this is called the soft part, but there's no notion of purely soft.
Okay, understand. Fine. Okay, thank you.
Yeah. Sorry, I forgot your question.
Yeah, I was asking about these Hilbert spaces. I mean, how
Correct.
are they defined and what does it mean that? I mean, usually a super selection sector is supposed to mean, maybe I should use the marks.
Yeah.
Is this on? No, it's not. Yeah, so I mean, typically when you talk about super selection sectors, it means that there is no process you can do that will take you from one to the other.
Yeah, that's
But
because
here, like the memory effect is measurable. So what does it mean to have these different Hilbert spaces?
Yeah, so usually in super selection sectors, you're right. There's no process that takes you from one to another one. That is because super selection is usually based on something that's conserved, which are like the super translation charges that Suvrat was asking about. So here,
Or it would be related to some thermodynamic property, like
some thermodynamic property that you cannot change by a physical process. Correct. So here I am saying is, like classically all these objects live in the same phase space, right? When we quantize on the phase space things, we put some norm. And then, this is the right, all these Hilbert spaces are the correct Hilbert space construction. I can explain exactly how you construct these if you'd like. But so this delta is not conserved. So it's not like a super selection sector.
But what I'm saying is that's fine. But if there is a process that is taking me from one quote unquote Hilbert space to another Hilbert space, then there are not different Hilbert spaces, right? What does it
Why
mean to
not?
have them different?
They're different in the sense that you'll have some field operators at infinity, some asymptotic field operators, and these Hilbert spaces are unitarily inequivalent representations of those fields. I'm not saying there is no unitary map between these guys. I'm saying the scattering that takes you from one Hilbert space to another is not a unitary operator on a fixed Hilbert space.
But if you can map like two different Hilbert spaces with some transformation, then that like they are equivalent.
Okay, so if I give you a Hilbert space of some dimension, it's always equivalent in that sense to some other Hilbert space of the same dimension. That's not the question. The question is, are they equivalent as representations of the field algebra? That's a different question.
But why don't you take the direct sum or the union of all of these and call that the Hilbert space? Then
Okay.
there's only one Hilbert space.
Sure, you can. So that's one way of, so if you take direct sum, for example, that was your original question. Okay. So now, suppose you do some process in which you get some memory.
Yeah.
If I do a small Lorentz boost, it'll give me a boosted memory. This depends on angle, so it changes, right? Okay. In a direct sum, that is not unitarily represented continuously. You can't do infinitesimal Lorentz transformations if you direct sum.
Maybe we should talk later.
Okay, yeah.
Sorry. Maybe there's a question from this thing. I'll ask later. Yeah.
Okay.
I'm asking, suppose you do the electromagnetic analog of that.
Yes, this also happens in
Yeah.
electromagnetism.
So that's, if I understand correctly, that is a shift of A0, right? The gauge potential gets changed,
Yes.
right, by a constant.
Yeah.
Is it possible to understand this defined Hilbert spaces in that context?
No, you run into the same issue that you have this electromagnetic memory and there's infinitely many of them. So you can do a direct sum that has other problems, but you can also try to say, I'll integrate over this infinite dimensional space. And the problem there becomes is in infinite dimensional spaces, usually you use what's called a Gaussian measure to integrate. And I mean, we showed that any Gaussian measure you pick that's Lorentz invariant will have most of the states with infinite energy. So you can try to make different Hilbert
So is the
spaces
problem
by putting
coming
these-
because you're changing the asymptotic boundary condition and you're thinking of fixing the asymptotic boundary condition and then defining the Hilbert space? Is that
No, so all of this is happening purely at the boundary.
that is true? But I'm saying if the A0 value changes, then it's like changing the asymptotic value of the field, right? Is that the?
No, so I'm saying that the asymptotic value here, if you're just looking at the outstate, right, it can be non-zero. That is not the problem. The fact that this delta is telling you that it doesn't decay at both ends, that is the issue.
It doesn't decay at both ends, meaning in the initial and the final results are different. That's what.
No, I'm not differentiating between in and out here. So let's just look at the out.
Just look at the out.
Let's just look at the out.
Scribe plus. So
scribe plus. So at retarded time minus infinity and retarded time plus infinity,
the values are different.
There's a difference.
Yeah.
And that difference is what causes, if they were both the same all the time, you would always be in like the standard Hilbert space, which is zero memory. So it's not that whether you're allowing some radiation or not, that's not the problem. It's whether you should be allowing this memory effect. And the claim is it is generated during scattering anyway.
Like if you are allowing all these different values of A0, right? And there are operators or processes that are taking you from one to the other, then what is the meaning of these different Hilbert spaces, right?
Depend. I mean, what kind of mean? I mean, if you want to say Weinberg's soft theorem is not true, that's fine with me. I don't, Weinberg might have a problem. I mean, if you compute an S-mate.
It will partly seem correct.
Sure.
It's the interpretation I think what is confusing.
Yeah, so I'm saying, okay, there is some operator is what you're saying that takes us from one Hilbert space to another. And I'm saying there is no operator that does that.
But there's
no operator.
Can I say, maybe Kartik, the issue is one of terminology. Maybe you're trying to be mathematically very precise. Okay. Usually, I mean, the way at least I think of it is I say what Raghu said, there's a direct sum of all these states of different super translation charge. Mm-hmm. And in that, you construct a normalizable state by various normalizable states by writing down wave functions. Mm-hmm. So there's just a, in your Hilbert space, you just have all of these sectors labeled by super translation charge, which you can decompose into spherical harmonics. And then you can write down an eigenvalue for each of them. And maybe what you're saying is that that's kind of a mathematically not very precise way of doing things, which is what you said about, representation.
I'm saying that is one way of constructing a Hilbert space.
Right.
I can do something else instead of direct summing over them or do harmonics and direct summing over them. I can do something that integrates over these memories. There's no natural way of doing it. I can just pick some infinite dimensional measure and integrate it. That's all. I can take the infinite tensor product, which is just a horrible non-separable Hilbert space. I can also do that. There's no obvious candidate for a unique one.
I would have thought there is, because that's what the dynamics is giving you, right? It's telling you that, you, as you said, the S matrix is conserved in all these different, this super translation charge is conserved.
Yeah.
And then you have these different super selection sectors. So
yes.
But okay, so you just add all the super selection sectors. And
if you direct sum,
yeah,
then you're in trouble, because you can only pick, if you're picking all the super translation sectors, which have all improper states, you have to integrate. You cannot sum over them.
Okay, I agree. I'm just saying I agree with you that maybe but that's the same as saying when you write the S matrix and momentum space, those are improper states. So you should always think of wave functions. It's the same level of problem, right? It's a but maybe you should.
Quantum space, we know, it's a finite dimension. So we know that integral measures exist.
Okay.
Infinite dimensions, I'm saying there is no obvious candidate for an integration measure.
Okay. Please continue. It's a countably infinite dimensional set, but please.
Is the problem really that delta is a continuous parameter or something? Continuous
It's a function on a sphere, so there's infinitely many of them. That is.
But if it was discretized in some sense, there won't be. So
no.
Is the issue separability of Hilbert space basically?
It's separability, and the other thing is, you want to implement something like a Lorentz transformation continuously, right? So if you had discrete memories, you can't Lorentz boost from one value to another, because there's some nice function on a sphere. So you want a continuous range of deltas. You can say, okay, I'll give up on some symmetries that I don't want. That's also fine.
Can I what is the precise definition of this F delta?
Okay, precise definition. Okay, I'll give you a rough definition, okay? Or I can write the whole mathematics if you want. The precise definition is you take a classical solution which has this memory, okay? You create a coherent state on top of it, right? Any classical solution, you can upgrade to a coherent state. Agreed? Okay. Now you can ask, can that coherent state be normalizable in the standard norm? And the answer is it's not. But you have a perfectly well-defined what's called a Gaussian state. So all correlation functions are determined by two-point functions. And then you can act on that with creation annihilation operators, which gives you a whole Fock space's worth, but living in a completely different place.
So if I take a psi in let's say F0 and try to find the usual S matrix, that psi out lives in this F delta is the point. Is that the...
In one of these F deltas or a superposition of them? Yeah, something like that. Yeah.
But that is a well-defined statement, right? That
Correct.
has no ambiguity.
Yeah. No. Any other question? Okay.
If I just give a mass, at least in the photon case, I can just give a mass like that. That's how we usually deal with. There's an extra degree of freedom.
Sure.
But at least in that case, there's a Hilbert space and so on.
Yeah. So for massive particles, this problem doesn't show up.
Yeah. So
massive scattering is perfectly fine.
And the statement there would be that let's talk about photons, because I don't know how to deal with gravity.
We can even do scalars. It's fine.
Okay. Okay. No, but the point is that there you could kind of calculate an S matrix for with the slightly massive photons.
Correct.
And then that is kind of well defined, right?
It's completely okay.
So now the only question is that mass going to zero limit, and then the fact that it has an extra degree of freedom.
Yeah.
Right. Okay. Now,
and you've broken gauge invariance and all that stuff, right? You have to be careful with that.
Well, gauge invariance is really not a symmetry. So whether it's broken or not is a...
No, the S matrix in the end should be invariant, no matter which gauge you picked.
Yeah, but if I just Higgs the photon, okay, and if I take a mass going to zero limit, I'll get something which is gauge invariant automatically, right?
Okay,
except for this extra mode, which is
Yeah,
the
you'll get some extra mode.
but the
light.
extra mode you would expect in an up, if you're if your mass goes to zero, it will decouple in some ways and so on. So is there a way of saying, like what these memories and these Hilbert spaces and so on, how does it look like when we do that?
Hmm. Yeah, I'm not sure you're allowed to do it continuously. Taking the mass goes to zero limit. I mean, even if you do, let's say, scalars, so we don't have all this gauge invariance stuff I'm talking about. I don't think it's true that the massive S matrix, if you naively take the M goes to zero limit, you're supposed to get a massless case.
The massless, the S matrix might not even exist.
Yeah.
But at least cross sections, I mean, inclusive cross section, this is what.
Okay, yeah, inclusive cross sections don't care about any of this.
Yeah, so maybe the point is that you should not define, like S matrix.
Okay, yeah, that is a perfectly fine.
I mean, that's what we usually do in PDE.
Yes, that is a legitimate point of view that we don't care about the S matrix because it has this issue. We should only compute inclusive cross sections. That's okay. So
that's the only observable, and S matrix is just an imaginary theoretical thing.
Okay, yeah.
So it doesn't exist.
Yes,
who cares?
That's a perfectly legitimate way of having that point of view is perfectly fine.
Then sorry, in that point of view, what is the physical observable in which memory will show up?
Nothing. In inclusive cross sections, it never shows up.
Yeah. So where will it show? Memory fetch.
If you only compute inclusive cross sections, memory will never show up.
Yeah. But what other experiment will memory show up?
Because in some sense,
matrix. If you take the cutoff to zero, it'll pop up again, right? So inclusive cross sections put some IR cutoff. They compute some cross section.
Yeah.
Right. After that, you show the cutoff to zero. Yeah.
Memory should come out in that process also, I think, right?
I don't think it does.
Can LIGO measure memory?
Okay, so LIGO.
I mean,
okay. LIGO cannot.
No,
PT,
something
PTA,
like LIGO can.
They're trying to measure it with PTA.
Yeah, so
Pulsar
what
time
is the experiment really? Is what like it's not an inclusive cross section if that does not show memory, but
yeah. So I mean, so the way we measure this, you have these detectors and they're oscillating around when a gravitational wave passes, and you're hoping to see a permanent displacement.
In these observations, if you want to think on terms of inclusive cross section, is there a way to interpret this as some limit of an inclusive cross section?
I don't think so.
But it should be an inclusive cross section.
Be writable in the inclusive cross section.
I don't know any theorem to that effect. So I will push back on that statement.
No, because I mean, just to say, I mean, at the end of the day, it's about probability, right? Like even in these two detectors, you're saying if you see this place, I mean, in the quantum theory, what you're asking is the probability that it is. So you can just think of starting with the detectors. What is the cross section for the detectors to give this place like this?
Yeah,
that's a cross section, right?
But you're computing. So when you say cross sections, you're computing cross section probability of measuring some observable. And my claim would be, I mean, inclusive cross.
In state and with without specifying other things, like that's what inclusive is. Then you partially specify outstate.
Yeah, you partially specify the outstate and
partially specified outstate.
Yeah, so partially specified does not include specification of memory. That's exactly what I'm saying.
I thought I said think of the detector as part of the experiment. And
okay,
you are partially specifying the displacement of the data. Right?
Sure.
That is presumably inclusive because you are not caring about what else is happening. You want to know what is the probability of the detector getting displaced by.
Yeah, so at finite time here, you will be able to formulate that using inclusive cross sections. But after the whole thing has passed, if you're asking what is the permanent displacement, you won't be able to answer that with inclusive cross sections, is what I'm saying. If there is a way, I would like to know it. I don't think so. I would like to see how.
No, just detector scattering.
Yeah.
You have in-state detector, on outstate you have detector plus something, some stuff, which I'm not talking about.
Sure.
Okay, that's what inclusive is, and something over all of that.
Yeah. But the other stuff, right, that we have said, oh, I don't know what it is, that includes this memory. So if you're ignoring that effect, you won't see the permanent displacement of the detector.
This I don't understand. Why would I just take a photo of the detector?
Yeah.
And if I don't take a photo of other things, I can see the detector displacement.
Sure, but like, are you saying that the out state has memory or not? Then if it doesn't, then the detector won't have anything to say about it.
No, but then the detector will not be permanently displaced.
Yeah.
Yeah, but if I see permanently like
Sure, yeah.
quanta data,
Okay, yeah.
then I can conclude that some memory effect happened.
Okay, yeah, that's fine.
So in that sense, this experiment is detecting memory.
Yeah, classically at least, that's what we're doing. You're saying quantum mechanically, yeah, you're saying in QFT, I should be able to see this in inclusive cross sections. I'm saying, okay, maybe I don't know how to do it. Maybe somebody knows. Please, someone show me how to do it.
No, I'm trying
like-
to say how, but anyway, but.
No, but I don't think inclusive cross sections can find you memory.
So can I make a comment, Kartik?
Yes.
Yeah, sorry. Yeah, so actually there is a way if you do inclusive computation, but you put an insertion of like a graviton operator in the far future. I mean, this is called this crossover formalism to get classical observables from amplitude. So you just start with instate and you do inclusive computation, and you can see that it's not an inclusive cross section, but it's an inclusive observable where you insert a graviton operator in the far future, and there you do see that memory turns out as a IRC observable. So
You're talking about this KMOC thing, right?
Yes.
Yeah. So KMOC is not computing the standard inclusive cross sections, and
it's inclusive observable, not inclusive cross section. I agree.
In KMOC, you see exactly you can see the memory, and what I'll be showing is kind of sort of a souped up version of KMOC where you don't take the classical limit.
Okay, thank you.
Yeah. But yes, in KMOC, you can see the classical memory. Yes, that's true.
KMOC, you can, you can kind of make it, the standard KMOC doesn't calculate inclusive cross sections, but it's not very difficult to include. It's just a Schwinger-Keldysh, and you can.
Loga, it's inclusive observable, so it is not cross section, but it is an inclusive. It's an in observable, of course.
Yeah.
All KMOC is in.
Yeah, but you can make it calculate inclusive cross sections, right? I mean, it's not like.
I am going to tell you about basically Schwinger-Keldysh and how to do it. Yes, in the full QFT without doing classical limits. I'm saying standard S matrix does not account for this. Okay. So there are so we've discussed other ways that are not in this list of how to do this, but the standard way is, one of them is inclusive cross sections, and you can compute actually many things. A lot of people like this Faddeev-Coolidge stuff, which is related to the question about super translation charges. So they did this in electromagnetism, and it wasn't phrased by Faddeev-Coolidge in this way, but if you look at what they're doing, what they're really doing is, we don't like this delta thing. It's not conserved. It's taking us between all these different memory sectors. But suppose we use some conserved charge to construct Hilbert spaces, right? So your Hilbert space now cannot change. Every Hilbert space is based on some conserved charge. So you can never go between them, right? And then the S matrix should be perfectly well defined. So that was the Faddeev-Coolidge construction, not phrased in terms of charges, but that's essentially what they're doing. And it works in massive QED. So if you have massive charged particles with QED going around, you can define these Faddeev-Coolidge Hilbert spaces. It's kind of annoying to calculate. You don't have access to LSZ reduction, strictly speaking. But you can calculate some amplitudes. It's sort of just annoying and difficult. If you do massless QED, Faddeev-Coolidge is spoiled because of collinear divergences. So what happens is if your charged particles are also massless, they start emitting electromagnetic radiation in the same direction that they're moving in. And if you try to do the Faddeev-Coolidge construction with these kinds of states, what happens is that the beaming of the radiation actually makes the energy flux infinite. So you cannot really use the Faddeev-Coolidge kind of states to do massless QED scattering. And if you try to do this with asymptotic flat gravity, general relativity, I'm not asking about other theories of gravity here, there are no proper normalizable Faddeev-Coolidge states except the vacuum. And as was pointed out, okay, these are not proper states. Let's use improper states, integrate over them. And even there's no natural, obvious, unique way of integrating over these super translation charges.
You say this about also classical Yang-Mills theory?
Yeah, classical Yang-Mills also has collinear divergences. So you run into the same issue, yes. But I mean, if I put Yang-Mills here, sometimes people say, oh, Yang-Mills cannot go to infinity, it's confined, blah, blah, blah. But
Not classical Yang.
yeah, you run into this memory even in Yang-Mills, and you'll get these collinear divergences if you naively try to construct these states. Yes.
But for gravity, there's a collision.
There's a collinear divergence in gravity. It's a much weaker singularity, so it's actually integrable. So it helps you compared to this massless QED. So you don't end up with this issue of, oh, I have some infinite energy thing. So this infinite energy is really coming because the collinear divergence cannot be square integrated. In gravity, it can be square integrated. So it's not the collinear divergence that's causing this problem. So for example, if you do linearized gravity to first order, this is a paper by Akhoury and Choi, I believe, where they did linearized gravity, and you can, they give the same argument, is that you can integrate, you can square integrate the collinear divergence in gravity, in linearized gravity. So there is no actual problem with infinite energy.
So what exactly is the proof of this problem that you are saying?
Yeah, so we showed this in sort of, if you try to do the full gravity. So you don't separate the linear and the non-linear parts of how much this, this super translation charge. So if we don't separate it, yeah, that's what I'm not sure of. At first order, you don't see it. I don't know if it shows up at some higher order. If it shows up at higher order, it'll probably be second or third. It can't go beyond that. But I'm not quite sure where it shows up or whether it's completely non-perturbative. Oh, that's a good question. It'd be very good to figure out if it shows up perturbatively or just completely non-linearly.
So in the gravity, you can just take like a. So I'm trying to understand the statement that there are no collinear divergences.
There are collinear divergences. They don't cause an issue because they're square integral. Correct.
Mm-hmm. And this can be shown for this can be shown even for, like, say, something like a shock thing in non-perturbative.
Yeah. So usually in electromagnetism, where P is the charged particle, K is the momentum of the photon. So here you'll see if these are both null, there can be a collinear object. What happens in gravity, so this epsilon is just a polarization tensor of K. So in gravity, no, it's not it. V. And the extra thing helps you. So, it really is sort of how the index structure of gravity versus electromagnetism works. But you'll see a soft divergence in both. As K is going to zero frequency, that will show up in both. But the collinear one is much nicer in gravity. It's still a divergence, but not all divergences cause issues. If it's square integrable, you're okay. Okay. Oh, no, my remote. Yeah, so this was where I was going to wait for questions, but I'll wait for questions still. People have more. So basically, to summarize, there's this IR divergence in the standard S matrix calculations. And the question is, okay, what do you do about it? So I'll tell you one way of thinking about it, which is related to this KMOC thing that was brought up.
Isn't going in the experiment like in inclusive cross-sectioning as you are saying. So why should we care about?
I didn't say you don't see it in experiment. I said you don't see it in inclusive cross sections. I'm saying this is a real physics thing. You will see it in experiments. Hopefully, pulsar timing array actually sees this classically, at least. Right? I never said you don't see this in experiment. I mean, then I would have stopped at the first slide. I mean, the quantum effect is very difficult to see. That's true. Okay, so the point of view I'm going to take here is we're not going to consider any Hilbert space as special. Okay. And this is sort of what is done in curved spacetimes usually, is what you say is I have some list of correlation functions of all my operators that are floating around. And every such list defines for your state. There's more conditions for it to be a physical state, like positivity and stuff. But given those things, you can see that any such, you can show, this is the GNS, it's called the GNS construction. Any such list of correlation functions can be viewed as a state in some Hilbert space, but it's not guaranteed that all such states can be put into the same Hilbert space. And by same Hilbert space, again, I mean whether they are unitarily equivalent representations of the algebra.
And these O's you'll take to be bounded operators?
I'm going to take a star algebra, so they'll be unbounded. So there'll be A star, etc. There's a GNS construction even for star algebras. That's where you're going with this. If you restrict me to bounded operators, I can't use creation, annihilation, or field operators.
Yeah, but that's the point, right? Like if you really want to be mathematically precise, unbounded operators can't be multiplied typically because their domains are different.
But, all the domain stuff is fine, just the same that happens in standard local QFT. There's no issue with domains. In general, you're correct. You can't multiply bounded operators unless you make sure about domains.
Really, whenever this algebraic discussion starts, you start by saying that the only operators you will consider are bounded operators, right?
Not necessarily. There are constructions that use star algebras. I mean, they're not super recent even.
I have another question. So in gravity, what would be these O's? Because you don't have diffeomorphism invariant local operators.
Yeah, that's why I said asymptotic. They're not local operators. In gravity, we're only considering the in and out operators at infinity. And that can be defined. You have a nice phase space sitting at null infinity, and you can directly quantize there. You don't know what the bulk theory is, I agree.
To define these things, you need not be at scribe plus minus.
To define which things?
These omega O1, 2n.
Oh, this is just a completely algebraic construction. If you just give me some algebra, I can write these things down.
So these O's can be taken to live anywhere, scry plus, scry minus,
sure,
space like infinity, future infinity.
Sure, this also works in the bulk. I mean, that's how people think about.
Yeah, but I wanted asymptotic.
Yeah, I mean, I'm only looking at asymptotically flat spacetimes, but sure, you can write these down in other places.
Okay. But just for the second statement, in GNS construction also, you find a unique omega, right?
No. You start with an omega, you start with a state and build a Hilbert space on top of it.
Exactly. That defines for you that gives you a unique choice of omega, right?
No. You started with an omega. You could have chosen some other one. And those will give you different constructions.
But it's not the same Hilbert space.
It's not the unitarily equivalent in the sense of the representations of the algebra.
Sorry, Kartik, can I try to translate this to my language?
Sure.
These asymptotic correlation functions are basically just the S matrix, right? So that's how I would think of it. The only thing I might have said is that, you put in the right in and out states, so that the right eigenstates of supertranslation charge, so that the correlator is non-zero. Is that what you're effectively doing here? You're saying, I mean, just to say it another way, let's say I looked at these O's in momentum space.
Yes.
Then many correlators might be 0 unless I have the right ket.
Sure. Yeah. I mean, a lot of this will be 0 just by conservation, right? That's
just by conservation. I see. So you're saying that, so maybe we think of some wave function or something like that. And then this list of correlators you will use to define that state, right?
Correct.
I see. Okay, fine. Okay, thank you. So in my language, I would say that you write down some wave function over in and out states, and this list of correlators basically picks out the correct elements so that you get a non-zero answer. And so rather than using the wave function description, you'll use this list of correlators for that same information.
Sure. Yeah. I mean, one could think about it that way. I mean, I'm very hesitant to use improper states unless I know how to integrate over them.
Yeah. I mean, you said this a few times, although I'm not sure what the problem is, why it's any more problematic than integrating spherical harmonics.
Yeah. Okay.
You have a charge for every L and M, and you write down a wave function for every L and M. So it's the same as writing down a wave function in quantum field theory. It's no more or no less than that, right?
Okay. Yeah. We can chat about it whether
it's
up.
Fine. Okay. Thank you. Yeah.
Okay. So, I mean, this slide is sort of just super abstract. I'll show how to actually calculate things with this. So now we're just saying, we'll just map by mapping of in and out states. I'll just mean by some map. Okay. Okay. Sorry. Good question. I should have mentioned that. So these field operators, there are two of them. One is that living on past null infinity, the other on future null infinity. So by in, I just mean these correlation functions for the past null infinity operators is given to me.
All of them are in the past.
No, but then O out is the out state which goes to the future.
So
this is not computing cross correlation.
So you're
between in and out.
So you're not allowing me to put inside omega some O's in the far past and some other O's in the far future. Is that the point?
I mean, you could define an object of that sort. I'm just saying.
No, but are you considering such things?
No. Right now, what I'm considering only is if I'm given in correlation function, so an in state, that's how you would call it.
So you have a data of, correlation functions.
On past null infinity.
Past null infinity. And you have data of, correlation function future null infinity, but no cross correlations.
No cross correlations, yes.
And then you're asking, how if I know the in data,
I can calculate the out data.
Out data. And that's what you call this whatever, super scattering.
Yeah, $. I mean, it's just a way to distinguish it from S, but you could use any symbol here.
So there is no you don't have the data of cross correlation. That's what I.
You don't have data of cross correlation, because in effect that would be asking for some global state for which you need to do the scattering in the first place, right? So here we want to do the scattering, so we can't.
But do you even assume that such things exist or not?
No.
So you don't even want to assume that cross correlators exist as finite objects.
Yeah,
you just want to assume that there are in correlators and out correlators, and then you just want to know what is the map.
What is the map between?
If somebody gave you the in correlators, how do I get the out correlators?
Yeah. So, I mean, that is very much Schwinger-Keldysh style. So if people have looked at inflation and stuff.
So, sorry, if I understood the answer to Loga's question correctly, these O's live purely on scry plus or purely on scry minus?
One or the other. I'm not assuming that.
I see. Then it's not Schwinger-Keldysh, right? Because these are just free fields. So these correlators have no information about the bulk. Like, these correlators exactly.
Yeah, we know these correlators exactly, but the way I'm going to compute, given an in, the way I'm going to compute out is like Schwinger-Keldysh.
So in is defined at scry minus and out is defined at scry plus.
Correct.
I see. So you give me a list of correlators at scry minus that defines in, you give me a list of correlators at scry plus that defines an out, and then you will tell us how to look at the dollar matrix between them.
No, I'm saying given an in, I will calculate the out correlation functions. The out is not given to you.
So given in, so you will define the state on scry minus and compute in that state states correlators on scry plus. Is that how one should think of it?
Correct. Yes.
Okay, thank you.
That is the doable computation. I mean, if both out and in are given, and I give, you ask for what is the amplitude to go between them, that's a much harder problem. I mean, I'll point out why that is.
I see. Okay.
Any other questions?
in itself.
No, the scattering depends on the theory.
Even omega in how to calculate omega out. That's what
Yeah, that's what usually is the S matrix,
Yeah,
right?
yeah.
And that's where the theory information lives.
So, okay.
No, but omega knows about the free state.
Yes, it does.
It doesn't know about the interaction.
Interacting, yeah, absolutely.
So dynamics will still come in, right? That's
But only knows about the massless, right? Omega in.
Yes, this is only
Omega.
massive. You can put in massive states and consider sort of tensor products and other states of that sort. But the massive
states is minus?
No. Massive states will come from past time like infinity. So, I mean, here, that's why, I mean, in and out include in of both past null infinity and past time like infinity.
But what about space like infinity?
Space like infinity data is given by what happens on Scry, because on Scry data, you can compute fluxes of quantities and reach spatial infinity. There's no physical field. I mean, unless you're doing tachyonic fields, there's no field that goes to spatial infinity. There is data there. I'm not saying there's no information or data floating around at spatial infinity, but it's in the place where null infinity hits spatial infinity. That's where all the data is.
Okay, so you're saying omega n is strictly speaking defined on Scry minus union time like infinity.
Sure, yes.
Past time like infinity.
Yes.
And
future
yeah. Infinities and past infinities. Okay.
Correct. Yes.
So can I ask you a question?
Okay, yeah.
So for different memories, you will have different omega out. Is that right?
No, right now I'm not putting omega out in any Hilbert space, but yeah, for different memories, the omega out will be different. Its correlation functions will be different.
Okay.
I mean, specifically, you can compute the 1-point function of the radiation field, so New's tensor. And if you compute its zero frequency limit, you should get the 1-point function of memory. And that will be different in different Hilbert spaces.
But from what you said, that memory will also be coming out of omega in itself, right? Because given omega in, you want to calculate omega out. And presumably that also gives the memory.
Yes. I will compute the out memory. So you don't need to send in any memory. So on past null infinity, there's no jump in the field. But then when you calculate what happens at future infinity, there will be a jump. Okay. So omega out, so that will come from calculating how the scattering works. Okay. It's not built in to the states.
So these omegas are effectively like density matrices. Right now, do you allow
they're density matrices. Yeah.
So the question is that, do you allow mixed states, or are you put some condition that omega in and omega out are?
No, I'm not putting any condition.
So you're really asking, you're starting with a general mixed state.
You can, yeah. I mean, I'll do the simple case where it's a nice state, just to show that you can calculate
in the past infinity, and you end up with some general mixed state and the future infinity, and you want the super operator which maps
between those,
the past mixed state to the future mixed state.
Yes.
Kartik, can I say this dollar commutes with super translation? It's a super translation is a symmetry of this dollar super scattering.
Yes. So what we were able to show is, if you assume that the super translation charges commute with this dollar,
right,
you basically reproduce a version of Weinberg's soft theorem,
right,
okay, up to 1 over frequency. So it's not diverging anymore.
Right. Okay, thank you. And that's the memory that will come out in omega out, or it's some,
yes.
Okay,
here I'm computing 1-point functions, so you won't be able to see the full endpoint structure of memory.
Okay.
But you can calculate. I mean, you need more computational effort to compute.
Okay, thank you.
Yeah. Okay, great. So I've introduced more symbols. How do you calculate them? To calculate them, I'll introduce one more symbol. So what we're going to ask is, if we look at the field algebra, which I'm calling A in and A out, A in is again at the past, null or time like infinity, depending on your field. And I want to define some evolution map. So without all this abstract business, if an S matrix existed, suppose you were doing a purely massive theory, this fancy dollar symbol is essentially the S matrix. And the evolution operator would sort of just be the usual Heisenberg evolution of operators. So given some out operator, I can use whatever S matrix I have calculated to rewrite it in terms of some formula of in operators. That's what the S matrix would give you. It'll also give you how to map states in the standard picture.
Evolution is like backward evolution. It takes out state to in state.
Yes, yes.
Out operators.
Out operators. So I've written it this way because I want to calculate in the end this guy. I want to say, okay, I want to compute the out correlation function of something, whatever that something is, right? So I need to be able to write that something back in terms of stuff I know from past infinity. So that's why I've mapped it this way. You can also map it the other way and do everything. Okay, so one way was, yeah, if you find some big basis that covers all your states, all these many Fock space states, you just say, okay, I'll just make some basis out of them, like the super translation basis that was being asked about. You can just compute even though this is a map, you can compute its components in this different basis. And you'll call them amplitudes, same as how usual amplitudes are just components of the S matrix in a basis. But to compute this, you would need to generalize LSZ reduction. If you look at the derivation of the LSZ reduction formula in the original LSZ paper, so this is not something that has been later on added in, LSZ assumes from the start that all your states can be created from the vacuum by creation annihilation operators, which means that it's assuming there's one Fock space to work in. And so if you want to compute some kind of amplitude stuff with this, you would need to generalize that. I mean, that is something we're looking at. But a simpler way is to say what I was trying is let's compute the out correlation functions. Let's not worry about amplitudes. I mean, one should worry about amplitudes. But for now, let's do the simpler case of can we compute some out observable one-point function? And what I'm going to show is that, yes, if you know how to compute this evolution map, you can. So finally, I'll give a formula for this evolution map. But that's the setup. So I'll define some evolution map that comes from actual QFT. And what I'm going to do is I'm going to start with some in state. I'll actually take a two-particle state, just for simplicity. And I want to compute some out correlation function. And for the operator whose out correlation function I want, I'm going to use exactly the memory. So an actual infrared observable. Okay. Finally, here's the formula. It's a bit complicated. I'll explain what this does. So this is sort of a formula for constructing interacting fields in the bulk spacetime. So here this works in any spacetime, but let's assume Minkowski spacetime for now. And what this formula is doing is given the free field operator and the interaction Lagrangian, it is constructing for you in perturbation theory a interacting field. Okay. One way to sort of see, if you think of these formally as exponential time-ordered things, this is just sort of a spread out version of that. So how does this formula work? So here you have the free field, which I've taken to be the in field that I'm sending in from past null infinity. And I've assumed, okay, any free field I've constructed has the same data. And then I'll patch it up to include interactions, basically. And suppose I want to compute the interacting field at nth order. Okay, I take n copies of my interaction Lagrangian. That will give me an nth order term. I split them into two parts, the n of them. One group goes in the anti-time ordered product, and the other group goes in the time ordered product. I sum over all ways of splitting this big group into two parts. And that is Bogle-Bose formula. One of the things to note, these time-ordered and anti-time ordered products are already, to compute this, you have to renormalize. So it's not that, oh, I've skipped over anything. You will get renormalization scales in some observables that you calculate. Okay. Yes, yes, it didn't fit in my slides. I only wrote one integral sign and one measure. But yeah, it's integrating over all possible places that you put the interaction Lagrangian in. Yes. All places, including J's. Yeah. This is in the bulk spacetime right now. Yes.
Specifying boundary. Sin of x is not quite just boundary.
No, I haven't gotten to how to get to infinity yet. I'm saying in the bulk, this is a construction of the interacting field in the bulk. We need to take this to infinity now. And that's what we're going to do next. So this is an assumption. So I'm going to assume the same thing that LSZ do. And what they actually do is, suppose you take a free solution, capital F, and in Minkowski spacetime, it will fall off as 1 over R if it's a massless field. You can also do this with massive fields, but I'm just showing the massless field case. What you do is you smear your interacting operator with a free field solution using the symplectic form, capital Omega. So for scalar theories, this symplectic form is just field, normal derivative of field minus opposite, antisymmetry. Okay? And what LSZ say is that this limit to far future, far past gives you the asymptotic operator in the theory. Okay? And in the massless theory, so here I've switched to scalar fields instead of doing gravity because I don't know how to do bulk quantum gravity, anything yet.
Well, in that same expression, like I have two questions. Like, what is this A prime? Because A prime is not your summing over. Second thing is, what is mod of? What do you mean by that?
Okay, so I've taken n number of L interactions, right? I've split them into two sets, A and its complement A prime. The set A goes in the T bar, A prime goes in. So suppose you had 4, right? So your L interactions is at Y1, Y2, Y3, Y4, right? So you can take A to be empty and A prime has all 4 of them. A can have 1, the other one can have 2, 3, and 4, all partitions. Mod A is the cardinality of A. So how many you put in the anti-time ordered. So every time you put something in the anti-time order, you pick up a sign. So one way to think about this is if this is e to the negative I something, at every order you get some sign. Okay. So I'm going to assume an LSZ style asymptotic weak limit. Now, this really is.
What to people I'm not familiar with this limit goes to psi plus omega psi f. What is it saying physically? What is this pi out of S and what?
Yeah. So you take an interacting field psi and you take a free solution, okay? And you compute its symplectic form. So usually
I should think of these as having some classical expressions as functions of coordinates.
Yeah.
Okay.
This is what you do. LSZ doing some since that let's say you have a positive frequency solution, negative frequency solution. You can take a Ron spin of that with the field.
Yeah, in the scalar field, this
in the positive frequency, and you take a limit and you get the negative frequency annihilation of it, and you pick up the negative frequency, get the.
What is this pi?
I'm coming to the right hand side. So this pi is an asymptotic field operator that you get from this limit. Okay. Classically, what it corresponds to is if you had a free field psi, that would also go as something divided by R, asymptotically at null infinity. That's how massless fields would behave. This pi is the retarded time derivative of this coefficient. It's like the New's tensor, but for a scalar.
It's not the canonical momentum.
At null infinity, it is the canonical momentum, at null infinity. But on a null surface, there's only one field really. There's never a field and its conjugate. There's only the momentum.
Shouldn't I think of some combination of them as being the creation operator? Like if, or the annihilation operator, shouldn't it have been phi plus I pi or something?
On a null surface, you don't have two independent fields. That's exactly what I'm saying. On a space-like surface, you're right. There's a pi and there's a phi. And you take some pi plus I pi or something.
What do you mean you don't have? Where does the other one go when you take the limit?
The other one is there. If you take its time derivative, you get this. But time derivative on null infinity is already tangent to null infinity. So you only need one of the data. You don't need both. I mean, this is true for any
this
null.
phi out of S is the creation operator or the annihilation operator?
No, it's the field. You can decompose this into positive, negative frequency pieces, which will give you creation annihilation operator.
No, in the out, you just get like
Sure. I mean, I'm just doing both of them at the same time, but yeah, you will get one or the other. Yeah.
I mean, this is the normal, let's say, mass theory.
Yeah.
Phi 4 or something. If you do that, the phi out will be the annihilation operator at out state. And
If you pick this F to be positive frequency.
Yeah, it's annihilation operator in the F state.
Correct.
Yes.
Yes.
F basis.
Yeah. If you
F
pick
is a plane wave, then it will be the momentum annihilation.
a plane wave of positive frequency, if you take
Plane wave of positive.
if you take plane wave of negative frequency, you'll get the annihilation operator. So LSE works in the same way for both.
The creation operator, annihilation operator for F.
Yeah, sort of asymptotically, how F moves to infinity. Okay. Any other question? Okay, now I have skipped a bunch of calculation in going to the next one. But what you do is you have this limiting definition of what your field operator at infinity is, and you have this formula for how to construct the interacting field in the bulk. And if you put them both together, sort of do some calculation, what you get, because this interacting field was computed in terms of a free field solution determined by the in data, you actually get a way of writing the out limit in terms of the in limit plus corrections due to interactions. So if there was no interaction, for example, this field would just go through as you would expect. Yeah, 1 to infinity, not 0, correct. Yeah, so that part I've taken out, the free field part. And this negative p square essentially is the equation of motion operator for a massless field. So if you do a scalar field, I mean, this will also show up in LSZ reduction. It's essentially the same reason it shows up. And this omega is the frequency because the operator here is the time derivative in the retarded time. And I'm using this operator because the zero frequency limit of pi is exactly the memory. And that's what we'll try to calculate. Okay, any questions? Yeah, I mean, ignore the total factors. They just come from sort of calculating exactly what the limit is. So here, if you compute exactly what the limit is, the 2 shows up. I mean, you can just say 2 pi is my operator if you want. There's no problem with it.
This equation, the second last line on the slide is the free answer. That's for the free theory.
No. The psi n is the interacting one.
Oh, okay.
So these are all the corrections from interactions. This is the free guy.
Okay.
So in the free theory, whatever you send in is exactly what will come out. There's nothing going on. Yeah, where the out is at 0 frequency, correct. Okay. So the way to do this is kind of similar to what you do in Feynman diagrams. So I'll show more pictures now. But you want to compute this and you expand it using Wick's theorem into normal ordered things and contractions. Okay. Here in Feynman diagram business, you always get only the time ordered product. So you only have one kind of object contraction to work with. Here, what actually happens is you'll get a contraction between things in the time ordered product. That will give you the Feynman propagator. You'll also get contractions for things within the anti-time ordered product. that gives you the anti-Feynman propagator, so reverse time ordered. And you'll also get contractions between the things in T bar and the things in T. That is the usual normal ordering contraction, which gives you the Whiteman function or the 2-point function in vacuum. Okay, so you have to take care of three different kinds of contractions in your Wick theorem expansion. Okay, so the way to nicely keep track of all this is the same thing you do with Feynman stuff. If my slide will go ahead, to draw diagrams. Okay, so here I've done this for a specific example. So I've taken a massless scalar and a massive scalar, and I've sort of written sort of a simple interaction between them. You can do this for QED with massive charged particles also. Okay, and what all this stuff is every vertex is an interaction vertex, same as in Feynman diagrams. So here, with the dashed lines, I've denoted massless scalar, and solid lines are all massive scalars. So every vertex will have one psi and two phis coming out. Okay. I have to keep track of where each vertex came from, because that decides in my formula which contraction I'm using, Feynman propagator or anti-Feynman propagator. So the white circles are all the vertices I put in the time-ordered product. And the black circles are everything I put in the anti-time ordered. Okay? I have to sum over all possible assignments of these white and black circle colorings. I've only drawn some of them. A lot of them go away because of kinematics. And this cross dot means sum over both white color and black color. So it's accounting for two diagrams in some sense. And any line that joins a white circle, white dot to a white dot, will be a Feynman distribution. It's a standard contraction in time-ordered products. Similarly, between black and black, it will be anti-Feynman product. And if you're going from white to black line, you'll put in the Whiteman distribution. Okay, those are the rules. I mean, this kind of diagram has been already. This is not something I invented. It's already there in Schwinger-Keldysh stuff. And here, I've drawn these diagrams for a very particular computation, which I'll show next. But yeah, as you can see, even for a very simple process at some fixed order in perturbation theory, the amount of diagrams you get in this business is much, much bigger. Especially if you have to sum over all possible colorings in every diagram, you kind of have to sort of, be more careful. Which is why I've only done this kind of calculation. I was hoping to get away with 3 vertices, but the answer turned out to be 0. There's no memory produced at that order. So I'll show you one of the diagrams, which is sort of the simplest one, which is this middle one right here. So I'll also explain what I'm doing. So I'm sending an in state, which is a 2-particle state of the massive pi fields. Okay. And I want to compute the scalar memory. So this pi out I had, I'll compute pi out and take 0 frequency limit of that, which is the scalar analog of memory. It's the scalar field jumping between 2 different values.
What is the memory field?
Massless scalar field can also have this memory effect where its value at negative infinity retarded time is different. Yeah, it's the value. So, sorry?
Yeah, some.
Yeah. So
coupling of the scalar.
Yeah. So the coupling was this. So massive squared times massless. So I'm treating this as sort of a toy QED in some sense. Yeah. So this is not a realistic theory. I mean, I agree. But we are not going to high enough order that the mass effect actually comes in. The change in mass of this guy comes in at certain order in perturbation theory. Right? It comes from like loop corrections. So at least the one that I'm calculating does not have the loop corrections. So the reason I'm doing this is because it's simpler as a test problem. The idea is to then actually do QED with this, not scalar.
So why does it have to get a mass? Can't we just put counter terms to make it massless order by order?
You can make massless at some scale and it will run
It'll run somewhere else. Yeah.
So the beta function.
The-
Make it massless if you on all.
I mean, the pole mass will be 0.
Technically, the pole mass 0, but then all the.
But that's what the mass here should mean, right? It should mean the pole mass is 0.
But then in other scales, you won't get like whatever. That's not always.
Yeah, the infrared divergence will go away, is what you're saying. Yeah, that's true. At other scales, I mean, depending on where you fix your mass. But I mean, in any case, this is just a toy example to avoid dealing with polarizations and fermions and gamma matrices.
Again, what's the out state you are computing this memory? So you have these two pies going in. What is coming out?
I'm computing whatever is coming out I'm computing the 1-point function of whatever the state I get is. I'm not doing scattering theories. I won't know the full out state.
It's the 1-point function of what?
Of the scalar memory.
Of the 1-point function.
Of the massless scale.
Of the
Yeah, massless. Massive scalar don't have memory.
And you don't observe anything else.
Yeah, I'm only computing this one thing, only the correlation.
Just the part state of the massive part.
Correct.
And then you're calculating the field like the expectation value of the massless.
Massless field, correct.
It's just fire. You're writing this delta. Just fire. 1-point function of the field itself, right? That is what you mean by delta out.
Of the massless field at
Yeah.
0 frequency.
Yeah, psi. What was your massless psi?
Right. Psi was the massless field.
Yeah.
The object you get at infinity is the retarded time derivative of its asymptotics, which is the pi that I was talking about.
Oh, okay.
And that at 0 frequency will give you this. So this delta is the difference of psi, or the integral of its time derivative.
Okay.
So that's really an infrared object.
So at this order, you don't see the log omega kind of correction?
Good question. So you're asking about the subleading part. Yeah. So that you won't see, I think, in the memory itself. You will see it when you compute correlation functions of the pi without taking the 0 frequency.
Well, the point is, if you go in the time coordinate, then the approach to memory, there is a 1 over retarded time piece, right? That's what comes out from these log corrections. In the frequency space, it's log omega, but you approach the memory in the time space.
The log omega is not the memory. The memory is 1
log
over
omega is not the
frequency.
memory, but I'm saying that shift, you can ask how it approaches that final.
Yeah, you can ask for subleading pieces.
Yeah, there's a 1 over u piece.
Yes.
So that you don't see at this order?
I don't know. So for that, because I've already taken the 0 frequency, right? So if I look at what's going on.
Log omega is still singular at 0 frequency limit, right?
Yeah, but because this is the limit of the time derivative, it's not log omega that shows up in what you're asking. It's omega log omega.
I see.
I mean, you're right. Those effects should be computed. They'll show after this in frequency.
Okay.
Yeah. So that's just an annoying calculation where you get more diagrams. I've reduced the diagrams by saying I've already gone to 0 frequency.
Okay.
There are 20 odd diagrams in this business.
I see.
Kartik, I'm missing something simple. If you could please explain. You know, in the beginning of the talk, you explained how there was these IR issues in this Hilbert space splitter.
Yeah.
Now you're saying you're going to define the in state in some way, and you compute the expectation value of an operator inserted on scri plus.
Correct.
Which is fine, but you know, if I'm not understanding why this calculation has less IR issues than just computing in state to out state on scri plus. You know, even when you compute the S matrix, you don't actually compute the full state on scri plus. You just compute the overlap with some particular, you know, maybe like 2 momenta or something like that, right? The full state is like into all possible out. You don't actually compute that. So I'm not understanding why this calculation is less subtle than just computing that. In fact, it seems that would be the square root of this calculation. It would be simpler somehow.
That would be the square root of this calculation if you had taken into account all the other states, not just the standard S matrix, which gives you 1 over frequency. Here I'm saying I'm not specifying for you what the out state is. I'm calculating its correlation function only.
So maybe you're saying because you want to compute this particular observable, which is the memory, it's hard to frame that in terms of an S matrix, and it's easier to say, here's an in state and compute the expectation value of this out state. Is that what you're saying? Should I think of it that way?
Correct.
I see. Okay, fine. But I see. But I could have computed that by maybe computing a 1-point function in the out state and then trying to integrate over that and extracting the same answer from there.
Yes, so you can compute the full 1-point function. That the reason I skipped that is that has many more diagrams. So if
I see, but isn't that 2 particles to 1 particle outside, like 2 in to 1 out, with some that makes sense? Yeah.
The outgoing line here with the P
Uh-huh.
is not some outgoing particle basis.
I understand it's not some outgoing particle basis. It's an operator.
It's an operator, yes.
But I'm wondering if I could have got the same information by computing the outgoing particle basis and then doing an integral, like trying to go to 0 momentum. Are you saying that wouldn't work?
If you do it in the usual S matrix way,
Yeah.
where all your states have 0 memory, you'll just get a divergence again.
I see. Okay.
Maybe I can say this is a bit like 2 particles going to 1 particle, 2
Yeah.
particles going to 1 massless particle plus anything.
Plus anything, yes.
Inclusive cross section for this.
Yes, sure, yes.
This is where anything you sum over.
Yeah.
Good. So it's really an right. And in fact, this probably you can write it exactly as an inclusive cross section, right? Because this you would have written it as in out, and then there's another amplitude here which is out going back to in. If you think of the contour that computes this, right? Because the contour is you define something at in, you go all the way to plus infinity, and then you circle back to minus infinity.
Yes.
And that is probably exactly as Loga said, just computing some square of something, which is the inclusive cross section.
Yes. Okay. So
yeah,
so that is correct. So in the formula that you said for the inclusive cross section, right, where you have in operator out and then the sort of complex conjugate of it, right?
Yeah.
So there, usually the out is assumed to be a standard Fock space state, right?
No, but you can do it. This is not an inclusive cross section. I agree. So, but this is like a, if I can call it an inclusive waveform, in some sense.
Yeah, it's a it's an inclusive calculation.
In the sense that you're summing over the out states.
Yeah.
Okay, but you can take in principle, you can just put an infrared cutoff. The standard way to do it is just to put an infrared cutoff.
Yeah.
Okay, just calculate this waveform, sum over the out states, and then, take it away.
Yeah. So, but there, if you've summed over all the other things that are going on, and there you have summed over in even the infrared things, then you will get the same answer, I'm saying. So I'm not sort of claiming something extremely radical here, but this is just sort of a very straightforward way of doing it without going through S matrix and then IR cutoff and then something else.
You can ask what is P hat?
So I've taken the 0 frequency limit. So P hat is the direction in which on an angle.
And what are Q1, Q2, Q3, Q4?
These are the momenta of so I'm sending in a 2 particle state.
Yeah.
Right. But I'm computing expected value.
Yeah.
So there are 2 copies of the state.
Q3 and Q4 are just Q1 and Q2.
No, you have to.
As numbers, they are the same.
No, I'm not taking. So you have to smear this over a wave function on all 4 of them independently.
This is like you have a 2 particle density matrix.
Yeah. Just to Loga, isn't this maybe just to say? Sorry.
I understand there's like a forwards evolution where there are these 2 particles with Q1, Q2, and then there's a backwards evolution.
Sure.
And sort of there's a ket and a bra.
Yeah,
in the ket you have Q1, Q2. In the bra you have Q3, Q4.
Yeah.
But aren't they in the same state?
No. See, you can think of the initial thing as a density matrix. Initial state as a density matrix. Okay. Of in the 2 particle Hilbert space.
Yes.
So that has Q1, Q2, Q3, Q4.
Okay.
Right. Q1 a ket has Q1, Q2.
Okay.
Yeah.
The bra has Q3, Q4.
Sure.
So then the density matrix is a function of this thing. So you will convolute this guy with that initial density matrix.
So you're just calculating some off diagonal element where you have some ket, psi1, some evolution operator, expect some operator, this delta, backwards evolution, and then a bra. Bra is not the same as ket.
Yeah, need not be.
Yeah, need not be. It could be. One more question I have is, could you remind us of the classical formula? If I was just doing classical GR, how is the memory related to the momenta of the ingoing and outgoing particles? What was I just forgot in the formula.
Here,
you turn on the light.
Yeah. So here you sum over so P being both in and out.
Okay, so shouldn't this formula that you get depend on the out momenta because the classical one did? Classical depends on what's going in and what's going out. Here you have summed over everything going out.
Yeah,
right?
so
what's the...
yeah, so here, this is some amplitude calculation, right?
Not amplitude, I'm just asking classical GR, if I did classical GR.
Yeah.
Like Ashok has done these calculations with some other collaborators.
Yes. So in
there's a formula for the shift that you have.
Yeah.
In terms of classical momenta of going and out.
Correct. So classically, if you send something in, what comes out is completely determined.
Yeah.
So your out momenta is determined by whatever in you sent.
Okay.
It's implicitly here. If you do the whole thing.
What interactions you have in the bulk is already also getting put in here. I mean,
Yes.
in this calculation.
Yeah, in this perturbative calculation. Yeah. So this is at fifth order.
Yeah.
The third order was 0.
Okay.
I see. Sorry, Kartik, can I just ask one more thing related to previous question, just to interpret this in my S matrix language?
Yes.
I would have thought you do 2 going to n plus 1 and then n back to 2. So this is not quite the square of an S matrix, but it's 2 going to n plus 1 and n back to 2 and sum over all n. Is that the correct way to think of it?
Yeah, in the S matrix language, yeah, I've summed over everything that was not this p hat.
Yeah, but what this additional p hat operator is doing is it's creating one more particle. So it's 2 going to n, like if I inserted a complete set of out states,
correct,
then it would be like 2 going to n plus 1 and n going back to 2.
Correct.
Right?
So in this diagram, I mean, one way of kind of interpreting it, the top piece is like the forward time evolution.
Understand. Yeah, fine.
It's some insertion of an operator.
Yeah, okay.
The backward. So this is usually how like Schwinger-Keldysh stuff is interpreted as forward evolution, insert operator, backward evolution.
Fine. And also the claim would be in the S matrix language also, it would be clear that this object is IR safe. This thing I just said.
Yeah, if you sum over all the other stuff that went away.
Yeah. Okay, thank you.
So Kartik, sir, just a related question. So this is really, I mean, it's really morally KMOC, right? It's,
Yes.
So I could have done this computation with perturbative S matrix without the Bogoliubov formula, and I still will get this answer, right? Just with the, maybe I mean the formalism that you explained before. Like I would not need to know that formula to get this answer, right? Just I could have just done S matrix computation and could still get this.
Standard S matrix, if you just do this, the states that you have to sum over in the intermediate, right?
Yeah.
Those have to be all possible states, including memory states.
I mean,
okay. Yeah. Thank you. Yes.
It's not like they have to be all possible states, because at any order in perturbation theory, you'll get only some number of states. So I don't think it's probably the same kind of calculation.
Yeah, I mean, I'm not.
Yeah, I think it's
I suspect it might even be easier because you'd only be computing Feynman diagrams with one kind of vertex rather than two kinds of vertices. But I mean, I might be wrong.
Yeah, I mean, I haven't seen if you can actually get this directly from.
Okay.
So actually, Kartik, just to say, I mean, the linear memory for gravity, we can get from KMOC directly with normal estimate. Like we can just compute it this way and we can see like, so you compute your H waveform in the far future at finite frequency, take the limit, just look at the residue at 1 by omega and you get the memory.
So doesn't KMOC do a classical limit?
Well, KMOC itself does classical limit, but I'm saying that the formula itself, before you take the classical limit is an inclusive observable formula, right? And so if you just compute the 1-point function for each mean, you don't take classical limit, if you don't want, and you can still take the omega going to 0 limit.
Correct. Yeah, I mean, if you don't take the classical limit, it will reduce to exactly what I'm doing.
Yeah. Thank you. Yeah.
Do you want to ask? So this formula, the fact that you've only written it in terms of the ingoing momentum, does it suggest that the classical expression, which I don't remember, but maybe Bubbly or Ashok can remind me, is written in terms of both in and out? But does it suggest that there should be a simplification of the formula to this exact formula?
No, this is only computing the expected value. I'm not computing 2-point functions, etc. So I'm not giving you any details. Even classically, morally speaking, you don't need in and out data to calculate anything.
Understand, but the formula that's simple is written both in terms of in and out.
Correct.
So if you're giving some formula that's only in terms of the in data,
Yes.
Shouldn't that suggest that the classical formula can be rewritten only in terms of the in momenta?
I mean,
But it depends on the theory, Raghu, right? Because the out momenta depends on in terms of what theory you consider. So that's the interaction details matter.
I'd say we do
by the
this
dynamics, yeah.
And this theory, I mean, presumably you can rewrite in terms of the out and in, and then we'll get the simple formula, right?
Yeah, but here the thing I've done is I've sidestepped computing what out momenta particles are actually going in, coming out, right?
Yeah, but the question is how, when we want to compare this with the known formula, right? Which is written in the in and out,
No,
the general formula for memory.
So that the general formula is when you assume there's some particle basis that's going out, right? Here everything, even if there's some wave function in the out, I've summed over all of that. So this doesn't give you detailed information about what is the particle content. I mean, you have to calculate each of them separately. That's one of the drawbacks of this compared to usual Feynman diagram. So I don't know. I know this state has this much memory, right? I don't know how many massive particles it has.
Additional insertions are
I could have added more things here and computed a 15th order diagram.
limit of some sort, which can be matched with current formula.
Yeah, can this be compared with that? I mean, it should be possible to compare this.
Yeah, I mean, I think you can, right? You just compute final momenta at this order in coupling, and then just it's like a linear impulse computation, and it will reproduce. I mean, this is in QED we can compare, and we do see that but it's perturbative, so yeah.
Perturbative, and not directly just this formula. You have to calculate what particle.
Yeah, exactly. Yeah, I agree. Yeah, I mean, final momenta you have to compute perturbatively and then compare. Yeah.
And if you have, say, given initial state, not classically, but in full quantum theory, there will be different final states, right? And this is calculating the average over all of those. Is that the point?
There will be one state.
One state, yes.
So I fixed Q1, Q2, Q3, Q4.
Yes.
Right. So to specify an in state, really you will smear Q1, Q2, Q3, Q4 with some wave function.
Yeah.
This answer will depend on that wave function.
True. Yes.
Right.
Yeah.
So here, if you change that in wave function, you'll get different expectation values because the out state is starting to change.
I think it's true that you're averaging over what came out, that n that you're summing over. It's like saying you're not observing what other massive particles might have come out.
In this calculation, I'm not observing anything about the massive particles. I'm only computing.
I mean, even massless particles.
Sure, yeah.
Came out, you're ignoring that, like you're summing over that.
No, but there's only one state here.
I mean, I understand, but that state can have different projections on different numbers of things.
Absolutely.
Coming over
Absolutely.
branches of those.
Sure, yes.
It's like saying, if your detector was not detecting polarization, you would compute an S matrix for the plus polarization
and
polarization,
sum over.
square the amplitudes and sum over that.
Yeah.
So here you are summing over
yes.
everything that your detector didn't see.
Yeah. So
everything other than this half time.
Yes. Yeah. So the detector is only looking at what memory came out. It's not caring about what other stuff came out.
Averaging over.
Sure. In that sense, yes.
Integrate against the momenta. Will you reproduce this? I mean, the available formula.
But you can't. You have to integrate with the correct amount of state that came out.
Yeah. But I mean, it's classical, so I guess it's more direct.
According to classical,
yeah.
There is a fixed final.
Yeah. But can you? There's no. It's predictable.
Classically, given an in situation, the out is completely determined by equations of motion. There's nothing funny going on.
Yeah.
Yes.
Then the interactions are very different.
Classically, there's no superposition of end states or
there
anything to average over.
Exactly. Yeah. So there you don't get expected value, right? You just get the observable. It's not expected value.
The question of comparison of this value with. Can this be tuned to, like, not just say that, okay, you are ambiguous to other things that you're observing, you don't care about that, you're agnostic about that. But rather than saying that, you just say that you observe memory and, let's say, two particles coming out.
So here you can add more outgoing things. You just have to.
It just complicate the diagrams.
Yeah.
I understand.
Yeah.
Yeah, because you're still summing over the remaining things that you are still agnostic about,
Yes.
but you are not fully agnostic. On
So
them.
the Schwinger-Keldysh KMOC kind of thing always computes inclusive.
Inclusive.
Yeah, that I understand. But you can put more insertions in the time fold
Yes,
towards
yes,
the
yes.
end, I'm saying.
Yeah. So I just did
And-
the simplest.
But
I
and
didn't-
that should match with the classical result.
Actually, one is, I mean, the classical itself is not a very well, I mean, I don't know, like, you mean like classical where all the particle, even massless particle is a classical particle limit or classical wave limit?
Yeah.
I mean, there are various kind of limits here. Classical itself is, but I guess, like, yeah.
Let's say 2-to-2 scattering with a memory. That calculation.
Where you have a classical, where massive particles are classical particles and massless particles are classical wave.
Yeah, something like that. Yeah.
Right. So in general, what will happen is that, like the particles will do something and then you'll get a spectrum at different frequencies, right?
Sure.
Okay. And you'll get like a massless wave going on in all directions. And he's just looking at the p hat direction, almost the zero frequency wave.
Yeah.
Right. The low frequency wave at some p hat direction. Okay. So then, like you don't care about all the wave that goes in the other direction. So you just look at that.
Yeah.
Yeah. So if you compare with that, you should match with this.
Yes. You can pick any p hat you want though.
Yeah. Maybe leading order you match and then, but then there'll be H bar corrections.
Yes.
Okay. And then, yeah. So that will be the corrections to that.
Also, if you want use a general density matrix, then it is possible to have uncertain final state, right? Because you have your initial state is now not fixed. And then you will presumably get an average over the memory formula, right?
Yeah. So here,
initial states.
Yeah, here I've picked sort of a nice pure state. So I just have to smear this over whatever its wave function was. But you can choose an initial density matrix if you want.
Okay.
Maybe technical. So in your formula, you had some pi out, pi in plus some corrections, right? This perturbative corrections. So if you also wanted to feed in the fact that the initial memory is not zero, it's some finite number. I mean, that formula tells it just adds on, adds as a number to it.
You can just
but here it adds like a vertex. So wouldn't that introduce more diagrams?
No, the vertex is only coming from, it's not coming from the in. So
vertex is not coming from. No, there's an in.
Okay. So I'm adding some memory here.
So pi in has no contribution to the diagrammatics.
No, the diagrammatics come purely from interaction rate. Even in usual Feynman stuff.
Yeah.
If I just ask, okay, what is the zeroth order field? You just draw one straight line. There's no vertex anything. It's all done, right? So the vertex only comes in the interaction Lagrange.
No, but the external leg. So delta out is giving you an external leg, right? And so is Q1, Q2, Q3, Q4.
Sure.
But now if you put an external leg for delta in also.
Yeah, so you wouldn't put
which is like specifying the initial memory, I guess.
No, so the field sort of, what particle content has how many creation or annihilation operators you use have that.
Yeah.
So the memory, what you can do is when in the next formula, here, right? Here you have to smear with whatever in wave function you sent.
Okay.
Right? So there you smear in with the correct memory wave function that you want. You don't insert memory as a vertex.
No, as an external leg, I mean. Like how Q1, Q2, Q3, Q4 are put in as external legs. And so is this delta out p hat, right?
No, delta out p hat is not the same kind of leg that this is.
It's not the same.
This is specifying the in state. This is telling you an out operator whose expected value you're computing. It's not telling you that there's a p hat sitting in the out state somewhere. So this is not an in-out calculation, right? So the way you would do it with memory is when you're smearing this with wave functions, you smear in the wave function which has memory that you wanted to send in. Does that make sense?
How will that modify the density matrix?
It won't modify the initial density matrix.
Yeah, the initial density matrix is changing.
But that has memory now.
No, initial density matrix is given, right? With memory, without memory, you give me.
You give me.
How do I specify that the memory in density matrix is my question.
There's no, like, the density matrix is density matrix. I mean, like, you just.
What does it? No, it can be a density matrix of two particle kind of state.
Okay, take a density matrix, compute it, compute expected value of in memory. If it's non-zero, that density matrix has memory.
Yeah. Yeah.
It's like, how do you know if this density matrix has energy? Well, you compute the expected value.
I agree. And in that sense, like this is a 2-particle density matrix, right? What you are writing.
Yeah. So maybe you want to add massless particles in the initial.
Yeah. So wouldn't that put a external leg for that particle also?
In the
inside. Yeah.
In the if you're sending in some particle.
Yeah. That's what I'm saying.
Yes.
The memory should be thought of as a external leg here.
No, the particle you're sending in, it's momentum.
External is a bit big.
Yeah.
In leg.
Incoming leg, like Q1, Q2, Q3, Q4, I'll have a Q5 or something.
Yeah.
With zero frequency.
Not just with zero frequency. You have to smear it with a particular nice wave function which has memory.
Also.
So put a dotted line coming from the left.
And then add more vertices.
Add more vertices, whatever makes your diagram actually function without being completely disconnected. Then when you smear the dotted line, you smear it with a wave function which has memory in it. It's the wave function that tells you whether something has memory. Otherwise, you could have smeared it with a zero memory wave function. It won't do anything.
Function which has memory. Maybe I'm not getting this point fully, but okay, I'll ask later.
Okay, so quantum mechanics, right? If I just write P, it doesn't tell me what the wave function actually is doing. I have to tell you the wave function when you integrate over P, right?
It's some wave packet.
Yeah, it's some wave packet. Your wave packet needs to have memory, not the P line.
Right? P is a particular state, right? It's a basis.
P is a basis.
It's a Fock basis.
Q is a.
Yeah, these are basis. So they don't have. So
they don't have memory or not memory.
The state is some linear some wave function in this basis.
Centered around some zero.
Which you convolute against the
momentum.
This basis
I agree.
Object.
So
right?
That is the definition of a wave packet.
Yeah. But this itself doesn't have any, this can be, it's for any general state, right? Any general state.
Any general state, you can have P1, P2, P3. Yeah.
Okay. Yeah.
Right. So, but now, okay. If you tell me what the wave function is, I can tell you whether the wave function has memory or not. I can't tell you whether P1, P2, P3 has memory or not.
No. I understand. You're saying I have to smear about a zero frequency.
Zero.
That's all you're saying.
Yeah. It should be non.
That I agree. And
okay. That's all I'm saying. So, yes.
Because it's part of the wave function, not pure.
Yeah. It's not in the line. You can put as many lines as you want, but if you want to send.
Q1 is about the Q1 about which you have.
No, so here I'm only sending in pure massive, right? If you want to send in memory, you would need, like you were saying, put a momentum here, which is massless. So a dotted line would also come in, right? But it's not just the dotted line that's telling you anything.
Yeah, I'll smear about.
You smear with a non-trivial zero frequency. Yeah, then you have sent in a state with memory. Yeah.
But my point was that the final answer is just this answer plus that.
Yeah, because it will be at higher order.
But you're saying it's just diagrams corresponding at higher order.
Yeah, if you put in one more line here, if you don't connect it to anything, it's not doing anything.
No, but now I have more possibilities for diagram levels.
Yeah, you have many more.
At this order only, I'm saying.
Yeah, but you have more vertices and
No, I'm saying at fifth order only. So there are 5 vertices.
You cannot connect it.
You're saying I'll not be able to connect at this.
So yeah, there's no connection at this order if you put in more particles. You're right. I mean, if you want to send that completely without interacting, then you're right. You'll just get that same thing plus this answer. But
correct higher order.
There'll be corrections at higher order in perturbation. Yeah. I mean, and even at this order, this isn't the only diagram. I've shown you one of, I put 8 here.
But by the way, this cross vertex, what do you do? Like you have the third kind of vertex.
Cross means sum over both the white and black colorings. So here I've already reduced a bunch of there are more diagrams you can technically draw, right? So everything I've made black and white here, you could switch the colors, right? But there are kinematics because each vertex has massive becoming massless. So there's a kinematic restriction on whether that's non-zero. And I've used that to reduce a lot. I've kept the ones that are not obviously reducible. And then I've computed sort of only one of those. You can calculate the others. It's not as nice answer as this. You'll get what you get in usual Feynman type integrals, dilogarithms, trilogarithms, all those things. You can show they are all finite. So this always gives you a finite answer that you can prove just by fall off of things.
What is finite? This loop is finite.
No, the final answer, if you include all the other diagrams which I have not explicitly shown, they give you some horribly complicated integral that you cannot write in some nice logarithm form, some dilogarithm or polylogarithm type functions. So it's you'll be left with an integral. That's just an annoying thing to calculate, but you can still show that the integral is finite. So this expected value will always give you something finite, no matter which diagram you're computing.
I guess coming back to this point again, so this is presumably the same as that, right? Once you put in for this classical process, what the final state momentum will be.
Yeah,
This should
presumably give the same thing, yes.
But you don't know if it does or not. I mean,
yeah, no, I mean, that's exactly what I'm saying, right? Because, suppose I'll have to ask how many momenta,
imagine that you throw in some two particles, right? To leading order, as you said, the final state is completely determined. It's classical. You know the interactions, so the final state will be completely determined.
Correct.
So you know the incoming momenta, you can calculate the outgoing momenta, and from that you can calculate the memory, right?
Yes.
So that should agree with this.
That should agree with this if you can do that calculation.
But why is it difficult? Because it's just low, first order deviation, right? I mean, you want to know how much the momenta deviate from the initial.
Are you saying classically or
classically? Classically.
Yeah, classically you should be able to calculate. And so here it is sort of, we don't know what particles are coming out.
But classically you will know.
Classically you will know, correct.
So if you just forget about this calculation altogether, you have a classical interaction Lagrangian and you have thrown in some particles, you know exactly how they are scattered. Yeah. And so that should give you this answer, right? If you do that calculation, then substitute in that formula.
Yeah. It won't give you exactly, this is the point I'm saying, is because here I've been agnostic and in some sense summed over all possible particle numbers that can come out, but classically you only get one.
That sum is dominated by one of the terms, which is the classical. And which is also approximately at least.
That might be.
I mean, there's no H bar here. So presumably there is a, I mean, this is the classical answer. How will you take the classical limit of this? Because
I've put all H bars to,
to
not complicate.
This looks like the complete answer, right? Is there a way to again take another limit which is classical here?
Yeah, good question. Whether I'll have to look at it. I'm not quite sure because I just to make my life easy, I put H bar to 1. But you're right. I should track it.
Yeah, because classical memory should come out as some limit of this, right?
Yeah. Okay. No, that's absolutely true. Okay. Yeah. Especially in the 1 point function.
Yeah, exactly. Yeah.
Yeah. Okay. No, I should look at that. Yeah.
Is this, I mean, since you have 5 vertices, is this 5th order in the coupling constant?
Yes.
But that classical answer will be lower order in coupling constant, right?
Depends on how H bar comes into the whole retarded product.
It can be, it will start at 5th order, you're saying?
Yeah, it could.
Some lower order.
So you have calculated if that memory is dependent on difference between the final and initial.
Yeah.
Right? And how much it deviates is already reasonably high for the mode.
Okay.
So there, I mean, you have to distinguish really carefully between order in H bar versus order in coupling constant.
I agree. Yeah, I meant order.
Yes, I should go look back where all the H bars I've dropped. Yes. Yeah, it's very much like KMOC. Yeah.
Taking classical limit like that.
Yes. Yeah, agreed.
They tell you how to take that.
Yeah. So, it should be there. It's not, I have to redo something. I just have to put all the H bars in the correct place.
But yeah, they scale the momenta and all also. At this stage, it's just loop counting, right? Shouldn't it?
Yeah.
Loop counting is H bar counting.
You can't do loop counting. This is a different classical. Particle classical.
But no limit has gone in so far.
No, but it depends. The answer.
Yeah, so the diagram is H bar.
Classical limit is not a very good way to talk about these things. Okay. So there's a let's agree that there's a particular classical limit we all are talking about, which is massive particles are particle classical and massless particles are wave classical.
Wave.
Okay. So let's not talk about any other kind of classical limit. There are many other classical limits. In that classical limit, loop counting is not H bar counting.
Yeah, I agree.
Yes.
So you can say h bar only, but what you keep fixed, right? That's the important. And you can say classical limit is h bar goes to 0, but what you are keeping is 6.
But this statement actually tells you what you're keeping. Taking mass particles, classical particle states, and massless particles.
Classical wave.
So you are in the frequency fixed for the massless particle and the energy fixed.
And the momentum fixed.
Yes. Right.
Sure.
Yeah.
And you take h bar.
Yeah. Yeah, so you can't naively take h bar to 0. Agree. Actually, that was the end. Take home. So basically, you can calculate infrared quantities, which is a lot like KMOC and Schwinger-Keldysh, like we've seen, and that's it. On time, Christ.
Maybe I can ask one more. If you had a non-trivial bulk background, like some black hole, blah, blah. I mean, again, asymmetrics kind of things will break down at some point, but these all make sense, whatever you're doing.
In principle, correct. In practice, how you calculate reaction to some non-trivial geometry inside is as difficult as you would find in Feynman diagrams, for example.
Yeah, but this inclusive observable, the memory and all as observables make sense, you're saying.
Yeah, here you only need the asymptotic flatness.
Yeah, let's
Inside
say
it could be
I
anything.
give you scry plus, I give you scry minus.
Yeah. So there the background will change the scattering calculation by quite a bit. Feynman propagators change, for example.
If there are no more questions, let's thank the speaker.
Thank you.
But even the fact that the percent scattering all particles is the fact that particles are possible that is just world like modeling them as excitation
and this will calculate the exception.